Now for the lecture content. As usual, we're a bit ahead going into next week's content, talking about more types of trees. Last class, I introduced the notion of a balance factor of a tree and how the AVL tree maintains a specific rule that every node must have a specific balancing factor, or a balancing factor of a specific value. And showed an example of a tree that's not quite balanced. So how do we maintain balancing? I'm actually going to keep up the suspense for a little while because I'm a bit disorganized this time. There are some strange bits in the slide such that either there's a mistake or I have no idea what I'm talking about. So I'm going to save AVL trees for later. I'm only going to talk about them when I know what I'm talking about. And for now, we're going to skip ahead in this lecture to the second, in my opinion, much easier topic. We're going to look at a new data structure called a heap and how it could be used to implement a useful ADT called a priority queue. So you already know about queues. You insert stuff in order, and then when you take a value away from it, it's going to be the least recently added value. Priority queues work similarly, except every piece of information has some sort of priority associated with it. And then when you dequeue an item from the priority queue, you dequeue the one with the highest priority. The real-world applications of this are pretty intuitive. Just like a regular queue can model a situation where people are waiting in line, say like at the cashier of a store, a priority queue can model a similar service situation, but where some customers have to be serviced sooner than others. You could imagine a hospital queue where the patients with the most severe conditions should be treated first. This is that kind of thing. As usual, the ADT is just the idea behind it, telling you what you can do with that data, saying nothing about how the data is stored. So the priority queue ADT gives you two operations. Insert adds a new entry to the queue with a given priority. And retrieve max removes and returns the item with the highest priority. Similar to that thing from the quiz answer key where like nodes were merging with their left siblings, but they could have just as easily merged with their right siblings, but we went to the left by convention. We're going to just arbitrarily say that the largest number represents the highest priority in the queue. You could specify this by saying that we're constructing a max priority queue as opposed to a min priority queue where the minimum smallest number represents the highest priority. But for simplicity, we're only going to study max priority queues, and then you could very easily figure out how to adapt this stuff to min. If I put this on an assignment, like, okay, I just explained what a priority queue does, now make it, it would probably be pretty manageable, actually. You can choose a data structure, so perhaps a linked list, array, or binary search tree, or even other stuff like hash tables. You can make the priority queue relatively easily, but it won't be as efficient as it could be. So I recommend going through this exercise for all of the data structures you know, but today we're just going to think about them for arrays. So how do you implement a priority queue using an array? I would probably, I just thought of a bad way to do it, and I'll use that to move into an okay way to do it. So here's attempt 1 at implementing this. I'm going to use an array to store my priority queue. When I insert an item, I'm just going to put it at the end of the array, O of 1 insert. Pretty good so far. And then when I have to retrieve the maximum item, I'm just going to go through the array elements in order and find the maximum and return it. Is my graphics tablet going to work? Yes. Oh, it's Pi Day today. So say I had to enqueue the elements in order 3, 1, 4, 1, 5, 15, if you want to be technical. And now I have to retrieve the maximum, which in this case will be 15. I can tell just by looking at it, but the computer can't. It's going to look through the array. Maximum is 3 so far. Maximum is 3 so far. Now the new maximum is 4. New maximum is 15. Reach the end of the array. Clearly, I should return 15. So I do that and remove it from the array. So in this case, I got constant time insert and retrieve max. How do you spell retrieve? Cool. Tried to guess this in your head before I write it down. I had to go through the entire array, did one operation for each. So it's going to be n. Okay, that's fine. If you're inserting way more often than you're retrieving, this could be a good idea. But if you're retrieving often, it's a bad idea because in practical terms, O of n is still kind of slow, and we can do better. So the slightly better idea, which now that I think of it more might not be that much better, is to sort the array. Whenever we insert an item, sort it such that the largest item is first. Or actually, it would be way easier to work with if the largest item were last. Sort it so that the largest item is the last one. And then when we have to retrieve the largest item, just take the last item. So in queuing 3, 1, 4, and 15 again, put 3 here, putting in 1, I'll sort it, putting in 4 again. Luckily it goes to right to the end, and so does 15. Then when I have to retrieve the maximum item, I can just take the last item. And in a larger array, we would keep track of the index of the last item, so we'd be able to retrieve the last one in constant time. So that's great. the time complexity of the insert operation is as bad as it is to sort the array. We don't really cover sorting algorithms in this class, but you might have analyzed some in first year, and if you're in the computer science program, you'll definitely analyze them in Comp 2080. A sort of canonical time complexity of a sorting algorithm is O of n log n. There are bad ones that take n squared. There are some really cool ones that take linear time but have weird trade-offs. But we generally say that sorting takes O of n log n time. So now this just has the opposite trade-off of the earlier one. Retrieving is now lightning fast, but insert takes longer than retrieving used to. So this isn't very good. We have to choose between we can have fast retrievals or fast inserts, but not both if we're using an array. The heap, as I'm about to show you, is a new data structure that'll let us do both of those operations in O of log n time. And that strikes a really nice balance between the two operations. They're both very fast. They could be faster, each one individually, but improving one would hurt the other in a way that's not worth it. And surprise, surprise, a heap is a special case of a graph. But before we get into that, here's another definition. A complete binary tree is a binary tree where every row, except maybe the last one, is full, and all the entries in the last row are arranged as far to the left as possible. So we see all rows except the last are full, and then for the row that isn't quite full, all the nodes are like to the left. Can't really think of a better way to explain that. So if I added a new node right here, that would still be a complete binary tree. But if I added a node here, that would not, because this one isn't as far to the left as possible. This is kind of like what you're proving on the assignment. If a complete binary tree contains n entries, then the height of the tree clearly satisfies h is less than or equal to log base 2 of n, which means that which means that h is also in big O of log of n. So now we get to the data structure. It's a complete binary tree whose entries are arranged in heap order. Heap order is where the value in each node is greater than the values in its child nodes. So take a moment here to understand the difference between heap order and the binary search tree property. Both are rules about how the parent node's values should relate to their child node's values. But the heap order is a bit less strict. In this case, the value in each node just has to be greater than those of its children. And it doesn't matter like what's on the left and what's on the right. They just both have to be less than the parent. So in this case, we could swap subtrees we could swap the left and right subtrees of the root. And that's a kind of interesting case because the nodes would still be in heap order, but it would no longer be a complete binary tree because we'd have an incomplete row with nodes that are around the middle or middle or the right, as opposed to all the way to the left as possible. So if we did that swap, it would still be in heap order, but it would no longer be a heap. Previously, as in the current assignment, we implemented a binary tree using a node with left and right pointers. But for a heap, we're going to use an array. Weird. Why are we going to do that? Well, I think it explains on the following slide. No? Okay. I'll just explain it right here. For reasons that you understand if you took Comp 2160 or any sort of low-level C programming course, and reasons that you hopefully will understand once you take whatever course replaces that, because 2160 is, I think, going to be discontinued next term. Memory access is actually super inefficient. Following a pointer to some location in memory is way slower than checking another index of an array. Actually, wait, this is advanced stuff. This isn't from 2160. This is stuff you learn about in the third-year course, Computer Organization, Comp 3370, with the memory hierarchy. So, yeah, I'm not teaching that. So for now, you'll just have to take my word for it that arrays are faster than any linked data structure. Additionally, and this is going to explain why we didn't just implement the binary tree using an array as well. The fact that the binary tree is complete in this case will actually give us a really convenient way to store the nodes themselves. With a linked data structure, it's pretty clear that like node would be a class and it would have a property for the left child and a property for the right child. They would both be pointers. It's intuitive, but it's not immediately apparent how you would store tree values using an array. In general, it's weird enough that we're better off just using a linked data structure for general binary trees, but a complete binary tree is a nice special case that makes it actually pretty easy to store this in an array. Yeah, this is just saying we put the data items in an array. Of interest, though, is that this data structure, this has nothing to do with priority queues, this is just a heap thing, specifies a way to avoid cases where you run out of memory. If you fill up the array, then you just copy the entire array into a new array that's twice the size of the old one. This isn't special for heaps. You could do this with any array, like if you're implementing a stack or a queue or something. So I don't know why we're just starting to do this now, honestly. A consequence of this technique for increasing the size dynamically is that some operations can get more expensive, so they can take longer than O of log n. So think about what you have to do to copy an array. You have to for each item in the array, take that value and add it to the new one. Yay. You'll have a for loop that iterates through all of the items in the array. And that would mean that the algorithm to do so would take O of log n time. Which means that technically the worst case time complexity of the insert operation is O of n, because the worst case is where you insert, fill up the array, and need to copy it. However, we're going to keep just sort of brushing up against advanced stuff and then ignoring it. It's possible to prove, like, not just trust me, bro, use your intuition, actually prove that these expensive cases occur rarely enough that the time complexity is still, on average, O of log n. The technique is called amortized analysis, and you can probably learn it in Comp 3170, which I might be teaching next term. I don't know. Okay, here's a heap. And we're going to finally figure out how we store the entries in the array. And it turns out the simple way to do this is breadth first order from the assignment. I'm just going to double check this. Yeah, cool. So I'm not going to fill in the entire array because it's on the next slide. But I'll do a visualization of the first couple levels. The root node is in index 0. The row after that takes up the array indices after that. And then we go with the following row. So perhaps if you have a pointer-based or a linked binary tree that is in heap order and you want to turn it into an array, you might use the breadth first traversal algorithm from the assignment. Ta-da. And then this gives us a benefit that I was talking about earlier, like why we were using a complete binary tree, or rather why that property of the binary tree made storing it in an array easy. And that's because since all of the nodes on the last level are as close to the left as possible, this makes it so there are no empty spaces in the array. You could imagine a binary tree that may or may not be balanced, definitely isn't complete, having a whole bunch of wasted space if you put it in an array. Oh wow, time flies when you're having fun, huh? I guess we're at the end of this lesson. Next week I'll keep talking about heaps and then go back to AVL trees. Have a good weekend. Oh, yeah.
Can I look at what I answered for my quiz?
Sure.